This is a continuation of part 1 of the McCabe-Thiele diagram. So the second part of this is to determine how many equilibrium stages we have to achieve this separation given these operating conditions. So what we start doing is we're going to start at our top distillate composition, and we're going to go horizontally from our material balance line to our thermodynamic equilibrium line, then down vertically to our material balance line. And we're going to continue this until we reach the bottoms composition. So I'm going to zoom in to show you how this is done. So if you're doing this on paper, you usually do a ruler or something. And I know these are thick lines, I just want you to be able to see it. But we go left to the purple line, our thermodynamic equilibrium line, down to our blue line, the rectifying operating line. And we continue to do this. And each of these points represents an equilibrium stage. So I know these aren't perfectly straight. So I've drawn all these out for our rectifying section, and I haven't quite gotten to that intersection yet between the three operating lines. When I do, this is what we have to do. And this is the reason I stopped drawing the lines to that intersection. It makes it a lot easier to see this and not make this mistake. We're switching from our rectifying section down to our stripping section. So now I'm drawing this vertically down to our new section, the stripping section, and we cross over. So now we're going to continue drawing stages from the equilibrium line to the stripping section operating line. And then we get down to the last one. We still continue all the way to the equilibrium line, but as you can see, the point that we need to reach is in between. So we want to determine how many equilibrium stages there are. And if I start from the top, we know we have a partial condenser. That's an equilibrium stage. So this is PC for our partial condenser here, then 1, 2, 3, 4, and so forth. And I'm counting this intersection here. So that's our 5th, 6, 7, 8, 9. So we have 9 stages in between our partial condenser. Our partial reboiler is also an equilibrium stage. But here in this case, you see that our last contact point is past our composition. So what we do is we could draw a new stage up from here and over. So this becomes our partial reboiler, and you can see that this 9th stage comes a little bit past the halfway mark. And so we're going to go ahead and say that this is 9.75 stages. This plus our partial condenser gives us a total of 10.75 equilibrium stages. Now subtracting out the partial condenser and subtracting out the partial reboiler, we see that we would need 8.75 trays to reach these conditions. Now obviously with trays having an efficiency of 1, having 3/4 of a tray is not the easiest thing to do, so there's other ways to achieve this exact separation. Or you would just use 9 trays and have a bottoms product that was a little bit more pure. Now to determine the optimal feed location based on this, all we do is look at our feed line and see where the transition occurred from the rectifying section to the stripping section. And you can see that tray 6 is still in the rectifying section, but tray 7 is our transfer spot. So that becomes our feed. So it's important not to say stage 7 and rather tray 7, since our partial condenser is an equilibrium stage. But again, the nomenclature is totally dependent on how you're referring to this column. What we're asked to do is determine the flow rates leaving the column, both the distillate and the bottoms product. We don't need this diagram anymore, so we're just going to do our material balances separately. So here's the schematic of the distillation column with the incoming flow rate and composition and the outgoing compositions. So we could easily set up 2 species balances to determine our flow rates out of our system. What is important to draw, which I haven't done, is the fact that we do have a partial reboiler that's adding a vapor back in, V bar, and we have a partial condenser adding a liquid, L, back to the top of the column. So this becomes D, this becomes B. We have vapor leaving the column and liquid, L bar, leaving the bottom of the column. So now I have my fully drawn schematic, and I can start writing my material balances. So I've written the material balances for both acetone and ethanol for our column. We can now solve for D and B. So our flow rate for our distillate stream D, 50 kilomoles an hour, and therefore a bottoms flow rate of 50 kilomoles an hour. The last part asked us to determine L and V bar, the other flow rates leaving the condenser and the reboiler. So let's start with L, the liquid flow rate. we know that L is equal to V minus D. We also know L over V, 0.868. So using our flow rate D and this ratio, we could solve for L. This gives us L, which has a flow rate of 329 kilomoles an hour. Now to determine V bar, we could do one of two things. We could either determine what the slope was from the bottom stripping line and apply the same methodology we just did, or we could take a different approach, and I just want to work through this other one. Based on the liquid being 329, we know that vapor therefore must be 379 kilomoles an hour. Now if you go back to when we determined the feed operating line, we had L bar equal to L plus F plus 1/6 F. We know the liquid flow rate. We also know the feed flow rate, so we could determine L bar. This gives us a total liquid L bar flow rate for the stripping section of 446 kilomoles an hour. Now L bar minus our bottom product, 50, gives us 396 kilomoles an hour. So that's another way, based on the feed operating conditions that we had before, to determine the other flow rates in our column. So you notice even though our product in our distillate is kind of low at the 50 kilomoles an hour, that's to maintain a continuous separation with 100 kilomoles coming in, our refluxed circulating flow rates are much higher.